Namaste. All right, good morning, guys. And what I wanted to talk about today is the concept of efficiency. All right. Um, Efficiency is the concept that, well, let me just say it this way: nature, whatever machine we make, we always get less work out of it than we put into it. Energy in any machine made by human beings, and you future engineers out there need to understand exactly what I'm saying. No machine ever made by human beings has ever been perfect. In fact, it seems to be like this law of nature. It's called the second law of thermodynamics, actually, that nature does not allow a perfect machine. And what that means is that you will always get less energy out of a machine than you put into it. Okay? In fact, nature says you can't even break into it, break even. You can't even make a machine where you get exactly as much energy out of it as you put into it. All right, and that seems to be a law of the universe as we understand the universe today. All right, in order to make energy is always lost somewhere in the machine. All right, what I used to do to demonstrate, were we in the classroom, what I'd be doing is I would get my pulley system, and usually I'd get like a double pulley system, all right, together, and I would lift some mass with it. And what we would do is we would measure. I used to put like one of those fish scales on it, okay, like that, and you could measure the force that I put into the machine, and we'd measure how far the distance that input force goes through, measure how far I pull the string versus how much force I'm lifting, call it my force output, all right, versus how high that goes, which is always less because the machine multiplies your force. And remember that the trade-off is always force for distance. You put less force in, you put more, you get more force out, but it doesn't go as far, okay? And if we would then measure, we would do this calculation in class, and we would measure the work we got out of a machine. The work out of a machine, I'll call that WO, divided by the work we put into it, okay? Which would be the force that we got out of the machine times the distance that force, so in other words, the weight that we lifted times the distance the weight was lifted, versus the force I put into it, okay? Versus the distance that I applied that force that I put into it, okay? And that's what we would do. And what would happen is this number up top there would always be less than this number right there. And students would say, why? And I'd say, well, did you hear the pulley as I was pulling on the string? Because the pulley would squeak a little and stuff like that. And they'd say, yeah. It's like, well, how did that sound? Where'd the energy come to make that sound? Well, it came from this input force right here, and the machine wasted some energy. All right, there was some friction between the string and the pulley and the axle that it's on, and that generated a little bit of heat, and so that energy came from the force that I put into it. So some energy was wasted with the machine. So energy is always wasted. In order to make a perfect machine, so you future engineers need to know this, you would have to, in theory, make a machine that has no moving parts. Think about that. All right. So, and how to do that, I have no idea. All right. That's beyond the technology that we have right now, and probably for the next several million years or whatever. But anyway, so the question then becomes one of how efficient can we make a machine? How can we make a machine that we get, how much work can we get out of a machine for a given amount of energy we put into it? To put this in perspective, and this is one of the reasons why we're going electric. Right now, the gasoline engine in your car is about at the high end, the 30% range. They're 20 to 30 some percent, okay, efficient. What that means is for every 10 gallons of gas that you burn in your car, only 2 to 3 gallons go into making the car actually move. The other 7 or 8 gallons are wasted as noise and as heat for the most part, and also internal friction in the engine and things like that. Okay, that's what we mean by efficiency. The new electric cars, electric engines, because they have less moving parts, are naturally about 45% efficient. And with the regenerative braking system that we have, in those vehicles, we can return energy to the whole system, and those systems are boosted into the 90% efficiency range. So electric vehicles are just a heck of a lot more efficient and than modern combustion engines. Now, that being the case, all right, to put that in comparison, the old steam engines of the 19th century were only 10% efficient. 90% of the energy was wasted as heat. That doesn't mean that these things aren't useful, because obviously these engines took civilization very far. With a steam engine, you could put it on a boat, and that boat did not need to depend on the wind, and it could go any direction it wanted, no matter which way the wind was blowing. You could put it on, you could make great steam engines, and we could transport things from New York City all the way to San Francisco on rail, and this took the world and technology into the modern age. And then the gasoline engine took it even further, and so on. So it's not like these things aren't useful, it's just that they're not efficient. And the challenge for future generations is to make machines that are more and more efficient. We'll never make them 100%, but we can make them better than 20 or 30%. Okay, so that's kind of the thing. So to give you an equation here, efficiency, which we'll just write as EFF, is defined as the work you get out of a machine compared to the work you put into a machine. And so work, it's also the energy you get out of a machine, because work is a change in energy compared to the energy you put into it. And because it's related to power, it's also the power you get out of a machine divided by the power you put into it. Any 3 equations, any 3 of these versions will work to calculate the efficiency of a machine. We're going to take a look at this one right here. So the efficiency is the work you get out divided by the work you put in. So it's the work is force times distance. So it's the force you get out of it times the distance that force works. The force you put into it times the distance that you worked with your force. Many students will automatically say efficiency is photo over feety. All right, that's just a student thing, right? But F force output, distance output, force input, distance input. And that's what it means. All right, so let me give you some examples so that I calculated ahead of time. So let's say that so I have a lever, let's say, and I'm going to put an input force of 10 pounds on this end, and I'm able to get 40 pounds out on that end. And let's say that I move my 10 pounds through a distance of 3 feet. And this weight over here that I'm lifting, the 40-pound weight, that only goes up a distance of 0.5 feet. How efficient is this lever? Now, in general, for, again, you future engineers, one of the things you need to know is that simple machines are actually usually pretty efficient, a 90-some% range usually, because they have only like one moving part. Okay, in general, the more moving parts you have in a motor, the less efficient it becomes. Okay, so that's something that if you want to be an engineer, you need to know that, because that's part of your livelihood. That's one of the secrets of the universe you need to know. All right, so how efficient is this? Okay, well, FODO, FIDI, okay? So my output force is 40. My output distance is 0.5 feet. Okay, now again, efficiency, because it's a ratio, all right, the units will cancel out. The efficiency has no units on it, like coefficient of friction, okay, like mechanical advantage. It's just a number. They're useful numbers, but it's just a number. It doesn't have a unit on it. Okay, so my input force is 10 pounds, and my input distance is 3 feet. Okay, so simple calculations: 40 times 0.5 is 20. All right, foot pounds, whatever, but it's going to cancel anyway. 10 times 3 is 30. Okay, 20 divided by 30 is 0.6 repeated, so I'll leave it as 0.67. Okay, what does that mean? Now, notice it's a decimal. And I'm not writing this on the board, so just listen. Your efficiency is always going to come out less than 1, because this number up on top there, because nature said so, is always going to be less than this number on the bottom, because you're always going to lose energy. Okay, so it's always going to come out as a decimal. Decimals are not that useful, so what we do is we multiply it by 100%. So we say that this would be 67% efficient. Okay, is how that works. All right, so it's usually, it's a simple concept, but it's a very useful concept, and actually for anybody, I think in the modern world, it's useful. All right, because you all use machines, you all drive your car. We talk about the efficiency of your home. How much fuel oil are you burning versus how much your home is keeping it in. If your home is less efficient, then heat leaks out of it, and that's an adult concern. So it's a good practical knowledge to know. All right, let me do another quick calculation for you. So let's say that we have a machine is 83% efficient. Okay, so some machine, and we know that it's 83% efficient. Okay, and we put so we're burning gasoline into this engine. We're saying that the engine's 83% efficient. We put 200 joules of chemical potential energy into it. All right, that's not pot marijuana, that's potential energy. So we burn some fuel, and 200 joules of chemical potential energy are released in the burning process. And what we want to know is how much work will we get out? How much mechanical work will we get out of the machine? Okay, so here we go. So we know that our EFF is now watch, be careful, because this will bite you in the rear end. It's not 83, it's 0.83. Okay, that's how I'm going to write it as. All right, and I want to know my work output. All right, or my energy output in this case. All right, actually no, my work output. Sorry. And the work I'm putting into it, okay, in terms of the change in energy of the fuel, all right, is 200 joules. Okay, so I know that my efficiency is work I get out of it, work I put into it. So what does that mean? That means that if I solve for the work output, that's my efficiency times my work input. Okay, and you can do that algebra. All right, so if I'm solving for that, just bring that up there. So which means, and let's make sure you got enough board space there, which means that this is 0.83 times 200, which is 83 times 2 is 166 joules. So I burn and I release 200 joules of energy from the fuel, and I get 166 joules of work out of it. Okay, so that's a typical efficiency calculation. All right. Okay, so I'm going to throw some efficiency problems out there for you guys to do, and see how you do. Talk to me during my office hours. Okay. All right. See you guys. Enjoy your apocalypse, and Goal us out.